Alrighty, so now we are on to a breakdown of numbers 9 through 16 in our assignment packet of problems where we are solving exponential and logarithmic equations. Let's get started. Number 9. Number 9, we have 5 to the 2x power equals 20. This is an exponential equation. Since it's an exponential, that means we need to use a logarithm to solve. X is in the exponent, we got to get it out. We're going to take the log of both sides because our base to a power is already alone. So we're going to go ahead and take the log base 5 of both sides. Now, why is it we're taking log base 5? It's because our base of our exponential is 5. They have to match. It's like salt and pepper shakers. You got to have a matching set. What are we taking log of each side? So it's 5 to the 2x, and over here we have 20. I showed you in the last video that log base 5 and 5 to the 2x basically cross out, and you're left with just 2x equals log base 5 of 20. When we're solving, a lot of the times you're going to be solving either just for the sake of solving, or you're going to be solving a word problem. When you're solving a word problem, it's probably going to wind up being a banking problem, something to do with time and money and rates. So if you are looking for a certain answer, you might end up punching it in the calculator and rounding. So no matter which way you end up simplifying and breaking this down, you will get the same answer in the calculator. So for that reason, I'm not going to go crazy with the 20. I'm leaving it. Yes, you could break that into 5 times 4, which then you could break into 2 to the second for the 4, and then the power. There's a ton you can do. Absolutely not necessary though. All we need to do is isolate x. We're just solving. So the next step, I'm going to get rid of that times 2 by multiplying both sides by 1/2. Now, even though I write it over there next to the 20, you have to remember, and let me just grab a different color pen. You just have to remember that the log base 5 of 20 is all packed up together. You can't multiply that 1/2 by the 20. It's not how it works. The 1/2 is just going to go out front. Got it? So over here, 1/2 and 2 reduce. We're left with just x, which is what we want, equals. So I can write my answer 1/2 log base 5, 20, or I just want to make sure it doesn't look like an O or another 0 and, blend in. Or I can write this as log base of 5 of 20 all over 2. These are the same answer. So we saw an example like this in the first set of 8 questions. But like I said, when I saw some people who worked this one out, when I assigned it earlier, a lot of people were really going overboard with the simplifying, which is great and super important, but it just didn't seem like you really knew what you were doing. It seemed like it was getting copied from somewhere. So I just want to make sure we focus on understanding the fundamentals before we move on. We have 15 to the 2n minus 3 is equal to 245. We're going to do the same thing we saw on the last example. Now, I'm just going to, I hate when the paper curls. I'm just trying to hold it down over there. Okay. Log base 15 of one side and log base 15 of another side. What am I taking the log base 15 of? On the left, 15 to the 2n minus 3, and on the right side, 245. If we take the log base 15 of 15 to a power, like we mentioned time and time again, we're going to have some simplifying happen. Log base 15 and 15, gonzo, left with just the 2n minus 3. Power property allowed it to become a coefficient, it's normal size, it's no longer a teeny little exponent. It's like when Pinocchio becomes a real boy. So the exponent becomes a real number. Not that it's not real, you know what I mean, real size. Log base 15 of 245. Another thing just to highlight while we're going over these, you can't have x in your answer when you solve for x. So definitely watch out for that. Just the passing thought I had. I did see that on a lot of people's papers. Next thing, we got to isolate the variable. So, and just happens to be my variable this time, I'm going to add 3 to both sides. It will not combine entirely with this. It'll just be on the side. Now I'm going to switch pen colors because I feel like I'm going to run out of room over here. So that cancels out, and we will have 2n equals log base of 15, 245, plus 3. This is all together. Now there's 2 ways we can take it from here. One way is we're going to divide by 2, and the other way is to multiply by 1/2. They are the same. It's all about how you write it, and you really need to think ahead a few steps, because when we start punching these in calculators, you do want to think about which way is going to be the easiest way to get this in the calculator, where I don't have to worry about, like, did I need parentheses? Did I type that in correctly? Is this giving me the right answer? Because that is a main concern when we're doing log problems. So if we divide both sides by 2, this 2 and this 2 will reduce down to 1. So that's totally gone. And over here, it's just over 2, and it is what it is. So you just want to make sure that over 2 is with the plus 3 and the log. The other way that this could get written is with the 2 out front. So I am actually going to switch pens one more time. The other way would be 1/2 out front, and then you want a big parenthesis because you're going to have a sum inside. That sum is log base 15 of 245 plus 3. So either of these answers is acceptable. They're both good to go. Number 11. For number 11, we see a subtraction between 2 logs. And while I could bring that log over, it does tend to make things a little bit messier in the end. So I'm going to implement the quotient property instead. So let's get started with the quotient property. This will become the log of 8 over 2x. Now I am remembering a few of the weird things people did solving this one, so definitely stay tuned until the end because you might be one of those people. Equals -1. Nothing's here written, but that doesn't mean nothing's there at all. That's actually at the base 10. And we have our single logarithm. We're in logarithmic form, and we are just going to swing it around and turn this into exponential form, because you need to use the inverse to solve for what's inside log. So that means I have to use an exponential. So what am I changing this to? This is log base b. So log base b of x is y. And I'm going to change it into b to the y equals x. Beautiful. B for beautiful. So that'll be 10 to the -1st equals 8 over 2x does reduce and simplify to 4 over x. So we can write it like that. Now, next step, what's 10 to the -1? 10 to the -1 is really 1 over 10 equals 4 over x. So this is where I saw some real interesting mathematics. Some people wanted to divide both sides by 4. Totally fine. I can dig it. Maybe you even, I'll rewrite it here, think of it as multiplying both sides by 1/4. I think that's even more beautiful. So here, 1/4 times 1/10 equals 4 over x times 1/4. So we're multiplying both sides by 1/4. Here, we are going to have 1 times 1 is 1 over 40 equals, a lot of people wrote x. It's not x. This is 1 over x. 1 over 40 equals 1 over x. Some people might have the logic to just say to themselves right away, then, okay, well, that means x equals 40, and that's great. You're really using one-to-one property in your logic if you think about it, because you're saying like, okay, 1 over 40 equals 1 over x. All right, well, that means x must be 40. Like, they're in the exact same place, both sides match otherwise. Another option, little arrow going this way as well, is you can do, if you remember from geometry, the product of the extremes equals the product of the means. So you can multiply 1 times x and you get x. You can multiply 40 and 1 and you get 40. And those are equal to each other. So in either case, we're really good to go. Okay, so you'll get 40 for x for this question. You can go back and check it. I promise it works. What else is there? If you ever solve and you get like your answer upside down, you're like, oops, I solved for 1 over x, not for x. In the calculator, there is that button that I've brought up to you guys before, the 1 over x button. If I were to punch this in the calculator, if I had, say, 1 divided by 40, right, which is 1 over 40, or I could have used the fraction button. On the calculator, I have that little x to the -1 button, which really is going to find me the reciprocal of that. So it's like, what's the reciprocal of that answer? 40. Granted, this one was really pretty basic. It does come in handy when you have big, gross decimals, you know? Oh yeah, and the domain here was all numbers greater than 0. We'll talk about the domain in a different question, though. Let's look at number 12. Here we have addition, and subtraction became the quotient property. So addition becomes a product property situation. So we're going to have log of, that's log of x, and that's log of y, and we want x times y. So it's really x plus 21 times x. You might not need that double parenthesis there if you're organized, but I think it's important to really show you what's going on. Again, don't forget, we have our invisible 10, and I'm going to multiply those. How do we multiply that? Well, I know you know how, but I also know that a lot of you are very guilty of not distributing this x to the 21. Believe me, I grade papers all day. So x times x squared plus, what do I see on the paper? 21. Make sure you multiply by everything. Do not rush. So x squared plus 21x is 2. Watch out when that's negative or it's not negative. Sometimes people lose the negative sign. In logarithmic form, and we need exponential to solve for logarithms, to solve logarithmic equations for x, and x is in here. I already have the idea that I'm probably going to end up factoring for this one, and hopefully you did too. B to the y equals x. 10 to the 2 equals x, which is x squared plus 21x. 10 squared is 100. This is a polynomial equation. More specifically, this is quadratic. How, let's go all the way up and around. How do you solve quadratic equations or any polynomial? We get them equal to 0. X squared plus 21x. This is really on the right. I'm just flip-flopping which side the 0 is on. You know, like I'm writing this side and putting the 0, you know, you get it. When 100 comes over, I know some of you get it, but some of you will still write the wrong thing. It's going to be a minus 100. So minus 100 equals, we'll squeeze 0. We need to factor this. I shared video links already with you guys for factoring videos, and I hope you took the time to watch those. I'm not going to show the work for factoring. I'm just going to get right to it. I'm going to kind of use the more empty method that sometimes people teach you. I showed you guys grouping and AC method. I have a leading coefficient of 1. And still squeeze that equals 0. Remember, if it starts as an equation, it stays an equation. What multiplies to give me 100 and adds or subtracts to give me 21? And I already know it's going to be 25 and 4. I want a positive 21. That means a positive 25 and a negative 4. And what will people do on multiple choice? Pick the one that's 25 and negative 4. But when you solve, what property do we use? we use the zero product property. That means you set each factor equal to 0. If I subtract 25, because I'm solving for x, what do I get? X equals negative 25. And if I add 4, x equals positive 4. Lovely. Go back up here. What is the domain? You always go back to the original problem for domain. When you find domain, you want to make sure you're not taking log of anything negative. So let's make a little space for some domain check-in up here. So if I want to find the domain, I need x plus 21 to be greater than 0. Subtract 21, x has to be greater than negative 21. Simultaneously, I need x greater than 0. Now you just use your brain and think, okay, I need to be bigger than negative 21 and bigger than 0 at the same time. So really, you just need to be bigger than 0. If x needs to be bigger than 0, well, looks like we have an extraneous solution. This is extraneous. It's not because the number is negative. If we only had x has to be greater than negative 21, and we had negative 4 as an answer, that would be fine because that's greater than negative 21. So remember, like, x could be negative. You just can't be getting a negative number for whatever it is you're taking the log of. A little strange. So there we go. X equals 4 is an answer to this question. Number 13. We have an exponential equation. We got to use log. Log base what? 8. Don't bust out the log base 2. Again, you're not wrong, but I never showed you that, and I'm not sure you understand what that is doing for you there. So we're going to take the log base 8 of both sides because we have an 8. Also, don't use natural log yet because we haven't had a conversation about that in our lessons yet. Log base 8 of 8 to the n plus 1 and 3. Log base 8 and 8 disappear. We're left with the n plus 1 equals log base 8 of 3. Subtract 1 from both sides. N equals log base 8 of 3 minus 1. We can't combine them because log can only combine with other like logs. Kind of like terms. Next up, this one looks a lot like 13, except we do have that extra step where we're going to have to add that 5 over first. You want to get the base to the power alone. Be careful when you're adding. A lot of careless errors that seem to be happening. 4 to the x equals 17. Some people tried to take the log of both sides here, or they thought the minus 5 was in the exponent. Make sure you look carefully, all right? Now we're going to take log base 4 of both sides. What is each side? Well, this side was 4 to the x, and this side was 17. What happens here? Log base 4 and 4 cross out, and we're only left with x. X equals, you could leave that just the way it is, log base 4 of 17. So if that seems a lot easier than what you had written down the first time you did this question, well, it's partly, I would say, if you're seeking out help from places that, again, they're not wrong, okay? I'm not saying that these other answers were wrong. It's just I can tell you don't understand, and I could tell it's not your original work. So you just really aren't being confident. And it's kind of hard to tell someone, hey, just be confident, believe in yourself. Like, I could say that to you a million times. Doesn't mean you're going to listen, right? You need the experience of knowing you're doing it right. And that's why I take the time to do these videos to show you answers. So you could be like, hey, I could do that, or I did do that. And you could feel good about yourself. And think of those as little deposits in your bank of confidence, okay? So give yourself a pat on the back if you understand. And if you did do something, or if you wish you had done it that way, you could just use a little confidence booster, okay? So little pat on your back, right? You deserve it. Let's look at number 15. All right, number 15, let's tackle this. If we're gonna do number 15, we need to probably begin by dividing both sides by 8. That leaves me with a nice clean log of x equals 2. Now, some people might stop here because it feels pretty finished. It's nice and clean and neat, but we're not done. We got a base 10, and it's not always 10. If it's not 10, there's another number. The reason I threw a lot of just plain logs at you at the beginning is because it seems to be the one that we're messing up the most is just plain common log. So I refrained from giving you guys like base 5, base 2, base 3, because I just really wanted to drill in that log by itself, plain log, is log base 10. So now a little loop-de-loop, and we're going to change this from logarithmic form to exponential form. 10 to the positive 2 this time. The other one was negative 2 in the example from the last set. I believe that's what it was somewhere. And we did have a 10 to the positive 2 somewhere as well. Equals x. And that gives me just x equals, what's 10 to the second? Not 20, 100. And again, when we're finding the domain, just because we have the space here, right? You take whatever it is you're taking the log of. Here I have just x. And you set it greater than 0 and solve for x. Well, x greater than 0, we're really done solving for x already. Here's 0, and we can be greater than 0. And that means with interval notation, if we want to be beautiful and fancy, we're right there. 0 to infinity. Nice. And 100 is definitely in there because 100 is way down here on the right, definitely in our domain. So our answer is acceptable. Let's do number 16. This one is nice and simple, nothing to do much, but there's our 10. 10 to the 2 is x. Do you see that this is actually the same question as this? 10 to the 2 is x, and that's just 100 equals x. We get the same answer. Still in our domain, same rule applies. But I'm going to throw a little bonus at us right now. When we solve equations, and I talk about this a lot, and if you plan on doing higher level math in high school or college, you want to have a good understanding of what it is you're doing. And I just try to give you guys everything I wish I had when it comes to having a good, strong foundation. So we're going to look at number 15 first. And number 15 was 8 log x equals 16. When we solve an equation, and like I said, I spoke about this in earlier lessons, anytime you're solving an equation, you're really finding when they're equal to each other graphically, where do these two things intersect each other if they were graphed on the same plane? So I'm going to slide this up because I don't need to see those other problems anymore. Let's just start off with getting ourselves a really nice graph set up on this page. Let's just tap my magic panda to create some real nice graph. All right, so I decided to come up, I guess the panda decided that we needed to count by some different numbers on each axis. So on the x-axis, looks like we're counting by 4, and on the y-axis, we're counting by 2. When we're graphing these two equations as a system, they're each their own equation. So there's this like hidden y equals for each one. So y equals 8 log of x. 8 is the vertical stretch. Log of x is the parent function, really, and the base is that invisible 10. Now, there's no plus or minus here, so my graph didn't move left or right, and there's nothing being added or subtracting at the end. So my h and my k are both 0, essentially. So if you like it like that and you want to write that out, go ahead. Y equals 8 log base 10 of x minus 0 and plus 0. Okay, so if I graph my log function, and I'm also going to graph the other equation. What's that other equation? The other one is y equals 16. Some of you might be thinking about how we would write sometimes the y equals in front of this squiggly bracket, but that was for piecewise functions. So for a system, you write the equations independently of each other, and you'll have y equals and y equals. All right, next. How do we graph each of these red equation is definitely easier. Y equals 16 is just a horizontal line. So here's where y equals 16, and I'm just going to go straight across and kind of use a highlighter to color code each of these and make my equations a little bit more bold so it's a little easier to look at everything. I want to graph my logarithmic function. The log function has an asymptote. I hope you remember what kind of an asymptote that is. I'm going to draw the asymptote for this graph in green, and I'll draw the actual function in purple. The asymptote is also related to the domain, so we are going to talk about a couple things at the same time. The domain of my purple equation over there, we take whatever it is you're taking the log of, and you set it greater than 0. So my domain is from 0 until infinity. Those are my x values. The parenthesis at the 0 is really showing me, just to tie it all together, where my asymptote is. My asymptote is going to be at x equals 0. And x equals 0 is actually a vertical line, similar to how y equals a number is a horizontal line. I'm going to go ahead and draw the function. Normally, I gave you a set of rules for graphing these, and the rules were that we're going to go over 1, up none, and we're going to go over the base and up 1. Unless there's a vertical stretch, then you go up 1 times that stretch. Over 1, up none is still going to apply. That's really close over here because I'm counting by 4s. My next point would be over the base, not from this dot, but from the origin 0, 0, or HK, wherever that might be. So I'm going to go over 10. That puts me right over here. And I'm going to go up 8. Now that's just 2 points. How do I get more points on this graph? If we remember, log is the inverse of an exponential. That means what we'll see is my distance away from the vertical asymptote will multiply by this number, the base, each step of the way. We're 1 unit away from my vertical asymptote. 8 units away because of that stretch. Now I'm 10 units away. 8 more units, I'll be at 16. What's 10 times 10? 100. So I'm going to be 100 units away. I'll be right there. If I go up 8 more at 24, I'm actually going to be 1,000 units away. So log is a very slow growing function, and a lot of the times you're not going to fit too many points. That's why I really just focus on these 2. Now, some people will draw their graph like this, but there is a bit of an error. You guys tend to miss this over here. You draw it like a square root. This is going down forever. So now I'm just going to go over this with the highlighter. So here we go. We have our log function and our horizontal line, and they both cross each other when x equals 100. And that's exactly what we said that the answer was. So when we're solving an equation like this, we're basically saying 8 log x and 16, y equals and y equals, intersect when x equals 100. If for some reason you needed the ordered pair, it's going to be 100 comma 16, but that's not what we're looking for when we're solving for x. We're really just looking for the x value. I hope that this gave you a visual so that you understand how the graph and the equations, how the graphs and equations are related to each other. Now let's look at number 16, which also had an answer of 100. Let's get ourselves a graph. All right, so we have ourselves a graph here as well. And this time, this graph is still being, on the x-axis, we're still counting up by 4 every 1 unit on the graph paper. But it looks like on the y-axis this time, 2 units are 1. So really each box is 1/2, whereas before each box was 2. So my first graph had it was sort of like the graph was actually compressed by 1/2 to make each box count by 2. And now this one is vertically stretched, so now each of these boxes is only 1/2. It takes 2 to make 1. My equations are up here, and we're going to look at it as a system of equations again. And I'm going to graph them using the same color setup. y equals log base 10 of x, which is really minus 0 and plus 0, and that is an invisible 1 out front for my vertical stretch, and I don't have anything affecting a horizontal stretch or compression. And that's something I should mention as well. A lot of people kept referring to the base as the horizontal stretch or compression when we did our graphing section. 10 is just the base. Just like in x squared, 2 is the power that makes it a quadratic. You would never say that this has a vertical stretch of 2 because of the 2 in the exponent. Do you know what I mean? So this 10 is not a horizontal stretch of 10. It really just determines the shape. The over base of 1, it determines that shape of the graph. Okay? The one underneath is going to be y equals 2. It's a system, so I'm going to put it on this little curly bracket, and I'll do color coordinating with the highlighters the same way I did in the last example. So I will go over this one with the purple highlighter, and I'll go over this one with the pink highlighter, and I'll draw my asymptote with the green highlighter, my vertical asymptote. So if I go ahead and graph this, it should be a little easier after the last one. This one didn't move anywhere. My domain is from 0 to infinity, so my vertical asymptote is just on the y-axis at x equals 0. The equation of a vertical line is always x equals a number, not y. I know the axes are the other way, so you have to remember it's the opposite of the axes. The y-axis's equation is x equals 0. The x-axis's equation is y equals 0. So it's a little sneaky and tricky. Graphing for a log, the steps we do are over 1, up none, and then over the base, which is over 10. Here's 10. I'm just going to go right there. Up the base. And remember, 1 is not really 1 unit up, it's a half. So up 1. The distance for log, the distance it is away from the vertical asymptote will continually multiply by the base. If it starts off 1 unit away, we're going to keep multiplying by 10. 1 unit away times 10 is 10 units away. Next one, because there's a 1 in front, 10 times more. So what's 10 times 10? There it is again, 100. 1 and 2. Y equals 2 is the equation of a horizontal line when y equals 2. So that's right over here. Again, we have another example where we can see that these two equations end up intersecting one another and they're equal to each other when x is 100. And that's why we had the answer of 100 for both of these equations. If we compare the two graphs, they are quite similar. I really am stretching this purple log function by 8. So this 1 unit up is now 8 units up, and then this one 2 units up stretched by 8 will be 4 units up. So this purple stretches by 8, but so does the pink. It's at 2, stretches by 8, and now it's at 16. So we're really solving almost the exact same system. It just sort of started off looking a little bit different. Hope this helps.